This week we will talk about clustering. So let's start with vector quantization. In supervised learning, we were dealing with data instances where class labels were available. So for every instance, we have a label. And from that, using, for example, parametric methods, we were assuming that the observations were following a given probability density function given by P of x given C, which is the class. And we assume somehow with parametric methods, for example, that in the basic case, there is one group of data per class. So we can assume, for example, that we were using a normal multivariate distribution, where for each class we have one distribution with a given mean, a given covariance matrix. And this is shared among all the data from the given class. However, in practice, we know that in some cases, the data of a class can fit in several groups. For example, if we talk about cursive writing, so unwritten characters, there are different ways of writing 1 versus 7. For example, we can write things like a 1 like this or a 1 like that, but this is not that different from a 7 like this or a 7 like that. And finally, there's that 7, which is quite different from the 1. But we see that we have, I would say, maybe 3 big ways of writing 7s, 2 big ways of writing 1. And these are from 2 different classes, and the difference between these subtypes of writing are not that different. You know, this one here versus that 7 here are not that different. And so modeling this well can be more complex than assuming one normal distribution per class. And also there is the notion of detecting intrusion in computer systems. You know, there is not only one way to intrude a system, to get into a system. There are many different ways. There are many different ways of using a computer system. So we cannot model this with one distribution. It's not realistic, not practical. The idea of clustering is basically to identify natural groups in the data. So basically we say, we are not looking at labels. In fact, we often don't have the labels. We are looking for identifying natural groups in ways corresponding to the given structure of our data set. So this is given simply from the data itself, the inputs, without making use of any labels. A simple example for doing this is what we call vector quantization. The idea is to say, okay, we have a space in d dimensions of real values. We have a space in RD. And we want, in fact, to partition that space into k regions, k different areas that are disjoint and correspond to the full RD space. So there are possible quantification using k reference vectors mi. So we can assign the data xt to the nearest reference vector. For example, just say, okay, we want to split this into k different regions, and we will define each region with a reference vector. And that reference vector should be somehow in something like the middle of a region. It doesn't have to be the exact middle, but it is describing the center of a region. And we assign a given x to the region corresponding to the nearest mean. So we have the nearest vector, the nearest mi, and we are looking to assign it to the nearest mean. And that's kind of binary. You know, we assign this to one region and only one. So bit correspond to the assignment of data xt to region I, and this value is 1 when it is assigned and 0 otherwise. This leads us to some kind of partitioning of the input space according to a Voronoi diagram, as we see here. So basically, you know, each kind of cell, which is divided by the red lines, is corresponding to an area that is assigned to the blue dot in the middle. So the blue dot is the reference vector. And we see that the split done in a Voronoi diagram correspond to the middle point. You know, for example, we have this thing here. We have this line here that is circled. So this line here is in fact totally in the middle, in between that point and that point. So if we are looking at that line, this is the point where the distance to each of the two blue dots that we circle that is corresponding to the area that are separated by that line. The line is at the exact same distance from these two reference vectors. Otherwise, on one way or the other, we are closer to one or the other of the mean reference vector. So what we are looking here is to do something like compressing that space into k reference vectors mi. And so each point in the original space is associated to one of the reference vectors. So we have discrete values. We are discretizing these each sample into one reference vector value. And this is kind of useful or relevant to the color map example. With the color map example, we want to apply this to the choice of colors for every pixel in an image. And basically, with current images, the usual way of modeling a pixel is to model it with the RGB, red, green, blue components. Every component is on 8 bits. So basically 256 tones of blue or green and blue. But we mix that together with these 3 values on 8 bits. We are able to define a specific color. So with 24 bits, we are describing a given color for a pixel. So if we want to transmit without any kind of compression, we just want to transmit the raw data for an image that is 640 by 400 pixels, which is a relatively low resolution image. That's something that was hot in the 80s, but now in the 2020s, it's kind of really low resolution image. Even though it is a really small, low resolution image, without making any kind of compression and assigning 24 bits for every of these pixels, we have more than 6 million bits to transmit. So that is a lot. And we can do more than this. We can do better than this. So the idea of this is to compress into a color map having 256 different colors. So we basically limit ourselves to 256 different colors that is put in a color map. And the point is that every pixel is referring by an index to one of these colors. So every color, of course, is encoded in 24 bits like we do with every pixel, but the image is not defined with the exact pixel colors. It's defined as an index in the color map, and we pick up the associated color at every index. So basically, the color maps with these 256 colors, 24 bits per colors, lead us to 6,144 bits to define the color map, plus an image that is where every pixel is on 8 bits instead of 24 bits. So basically a factor 3, we are 3 times smaller. So the image is encoded basically on a 2 million bits, 2 megabits, with a gain of approximately 3 to 1, because the color map here is kind of neglectable in the count. So we are able to compress it into having the same image with 3 times less information required. So that's nice. The loss, or I would say the counter effect of that is that if there are more than 256 different colors in the image, we will lose some information. There is a loss because we cannot describe all colors exactly. And so the point here, the problem is to choose the colors that are minimizing a certain criterion. So what are the right colors to use in our color map to properly encode the image with the minimal loss? For that, we are using what we call the reconstruction error, which we saw before with autoencoders, and maybe not directly, but we can apply the same kind of things with principal component analysis. So the idea of the reconstruction error is that we are looking at the difference between the original value. Here it is the pixel, the value xt, which is basically one image with its pixel. And I would even say here it's not that far from using, I would say, every pixel, whatever, that's not important for now, but the reconstruction error is looking at the difference between the instance and MT. Here it's the mean vector, that is its representation. So if we say that the real color is given in xt on 24 bits and the encoded color in the color map is on MI, which is also on 24 bits, but the choice of the reference vector may be different from the real value, and this is what we are looking for. We're looking for to minimize the loss in terms of approximating xt with a given mi that is not exactly xt. So we are doing some kind of compression by clustering. Here you see we have a x that is can be seen as 1 pixel, but can be many things. So we have a reference value that is given by x. This is what we want to transmit, but we don't want to transmit the x because it might be big. We want to transmit its compressed value. So here the compression value means to assign, when we are talking about vector quantization, we are assigning an index corresponding to one of the mi, m1 to mk. So we have k different possible values for as index from 1 to k. So we pick up the right index and we transmit that index only. And then we are assigning the value of x, which is x at here, as the one corresponding to the mi, because we transmit the index I. This allows us to pick up the mi corresponding on the decoder side that is assigned directly as the x hat. And our point is to say we want that x hat to be as close as possible as the original x. Of course, with only one x, we can do perfect encoding. The point is that we want to transmit many of these. And so we want to have the difference between the x hat and the x to be minimized. We want to lose as little as information as possible.